Hi everyone. We're going to look at how we are going to revise the atomic model. And remember, we ended our last time with the idea of Rutherford's atomic model. Now, with Rutherford, he used again that gold foil and he shot alpha particles at it in order to figure out that, for the most part, the center of the atom is going to be very densely packed with positive charges, and it's surrounded by mostly empty space where the electrons stay. Now, it does explain a few simple properties of the atom, but it couldn't explain a lot of the chemical properties. So, one of the big things it couldn't explain was the idea where metals turn different colors based on how hot they are. So originally you would have a color similar to, this dark gray color. As it gets a little bit warmer, it turns to a red color and then finally a yellow color, and at the hottest point it is white hot. And so it couldn't explain why you got these different colors based on how hot it was. So Rutherford's student, Niels Bohr, decided to develop a new atomic model. He changed Rutherford's model to incorporate some discoveries about how energy of atom changes when they absorb or release energy. So anytime that an atom is releasing energy, it's actually going to emit light. That's why we get fireworks, actually. So with Niels Bohr, he figured out that each possible electron orbiting this model has a fixed energy, meaning whatever it starts out with is how much it always has. So a fixed energy can have different energy levels. So what the idea there is, if you have your nucleus here in the center, an electron can be only fixed distances away from the center of that atom. And these different energy levels are called quantum. And so the amount of energy required to get from, say, the closest spot to the next energy level out requires a specific amount of quantum energy to get to our next location. The same can be said if it wants to drop down from a higher energy level down to a lower energy level. It's going to have a fixed amount of energy required to move that electron from one energy level to another. So the best way that I can think of to show you how Bohr's model works with this quantized energy is the rungs of a ladder. So electrons in an atom can't exist between different energy levels. Just like if you were to go up this ladder, you couldn't magically hang out in the middle between this first step and this second step. You could either be on step 1, or if you took in some energy, you can be on step 2. There's no way to hang out in the middle where there's no rung of that ladder. So the amount of energy required is unequally spaced in our ladder. So you'll notice down here at the bottom, the amount of energy to get from our first rung to our second is fairly large. However, the closer you get to the top, it requires less and less energy to get from one rung to the next. So in our atom, this is very similar to what we see. Here is our nucleus, just like the grass. And to get from our nucleus to the first rung, this is where a lot of our electrons are going to hang out because they are the closest to the nucleus. Now, if it absorbs energy, so means it takes it in, it can go from the first step to the second step. And it can also absorb more energy and continue to go up this ladder until there's no more energy being, or not enough energy being absorbed. Now, if you were on that top step up here, so this would be on the 4th step where we stopped, and you got tired and you couldn't go up any higher, you can emit light. And that will allow you to go down the rungs of our ladder. So this energy level is unequally spaced, and they can't exist in between different energy levels. You have to be, like on this ladder, on one rung or the next, nowhere in between. So overall, Bohr was able to improve on Rutherford's idea of the atom to explain why heated metals and different things of that nature are able to give off different colors of heat or different colors of light because of that quantized energy, meaning you have specific steps in your ladder. You're able to see different light coming from each metal. From there, Erwin Schrödinger created a mathematical equation to try and explain this idea of the electron. And he came up with something called the quantum mechanical model. The quantum mechanical model is very similar to that of Niels Bohr's model, where you have specific energy levels that your electron can be residing at. So if you remember again, if you're in the center, the electron is going to be in one of the areas, specific areas surrounding that nucleus. However, the big difference is it does not specify the exact path the electron takes around the nucleus. It just gives you a probability of finding the electron. So if you were to look at this picture down in our right hand corner, the darker the region, so here's our nucleus here in the center, the darker the region, the more likely you're going to find that electron. So here are some really dark areas along with this central area here. That says that it is most likely going to be found in that region. Just like if it is 8:19 on a Monday morning, you know that most likely you are going to be at school. However, it's not a guarantee, right? If it was a day that you were sick or maybe had a field trip, you wouldn't be there. However, most likely you would be here at school. The quantum mechanical model is, again, that probability of finding that electron within a certain area. And it's usually shown as this pretty electron cloud, where the far out region out here around the outside is lighter in color because it is less likely to find electrons. Whereas the closer you get to the center, the darker it becomes. And the likelihood of finding a electron is fairly high, so it's going to be darker. So the more dense the probability of finding that electron, the darker it will be. So overall, our quantum mechanical model is very similar to that of Niels Bohr, where you have the quantum mechanical or the quantized energy, so you can only go up specific rungs of that ladder. But unlike Bohr, this quantum mechanical model doesn't specify any exact path. It just gives you a probability. So some solutions that Schrödinger gave were to show the energy levels an electron can have. So for each energy level, Schrödinger created an equation, which you will never have to know, which leads to an atomic orbital. And an atomic orbital is simply a region of space where you're most likely to find an electron. So energy levels, again, we're back to our ladder idea, are going to be labeled with a principal quantum number. That's a really fancy way of saying 1, 2, 3, 4, and 5. The closer you get to the nucleus, so remember our grass here is the nucleus, the closer you get, the number will be closer to 1. The principal quantum number will be close to 1. So if we were to label our ladder here, you see the bigger the number, the farther away I get from my nucleus or the ground. So principal quantum numbers for an atom are the same thing. The closer you are to the nucleus, the lower your number is. Now, for each of these principal energy levels that are bigger than 1, there are several sublevels. And these subatomic orbitals are denoted with different letters. The first one's pretty easy. S is our first type of orbital, and it means it is going to be a sphere. So the way I remember it is S, and our orbital, or our subatomic orbital, is going to look like a basketball here. However, the next two are a little bit more difficult to remember, but the p orbital is going to look a lot like a dumbbell. So you see it kind of like a figure 8 pattern here, but it looks a lot like a dumbbell you might find at the gym. And the d orbital is going to look like a butterfly. So if you wanted to, you could draw a little antenna out of here and you would see, hey, that looks just like a monarch. So these just show that the area in which you will most likely find an electron. Now, the numbers and the type of atomic orbitals depend on where you're at on our ladder. So remember that our ladder is our principal energy level, and that is going to tell you how many different types of atomic orbitals you're going to have. So here we have n equals 1. That means there's only one sublevel, and lucky for us, that sublevel is a sphere. Now, the maximum number of any orbital, so max number of electrons in any sublevel, is going to equal, oh goodness, sublevel is going to equal 2 electrons every time. So since we only have one sublevel here, you only get 2 electrons. As you go down, you see that once we hit something like the principal energy level of 4, you have 4 subatomic levels, and you have your S, your P, the D one that looks like a butterfly, and then F, which I can't even draw. So there are lots and lots of different sublevels that we run into. For each of those given principal energy levels greater than 1, there's always going to be, again, at least one S sublevel. You're also going to have your p orbitals. You can even have d orbitals. Now, notice the difference between these pictures. Our s orbital is always going to be on one plane because circles go in all directions, the x, the y, and even z. Now, unlike our sphere, our dumbbells, or the p orbitals, can lie in the x plane, the y plane, usually that one goes up and down for us, and the z plane, that one's the one coming out of our paper. And here it gets even more tricky. Thankfully, you will never have to draw them. Okay, you don't have to worry about that. But what you do have to know is that each one of these sublevels for D holds 2 electrons. And it's a way of organizing our electrons so they aren't very close to each other and repelling. Remember, like charges like to push away. So anytime we have these principal quantum numbers, they're always going to equal the number of sublevels within that principal energy level. So remember, our n equals 1 has 1 sublevel. The number of orbitals in a principal energy level equals n squared. So if you were to look back at our idea of n equals 1 with 1 sublevel, it would be 1 squared, which equals 1. The maximum number of 2 electrons can occupy the orbital. So we remember, look back at this one where we had 2 electrons in each one of those orbitals. But overall, in that D center, we have a total of 2, 4, 6, 8, 10. And finally, there must be a maximum number of electrons that can occupy it. So that's using this equation. So if we went back up to our n equals 1, 2n squared is 2 times 1 squared.